Alright, I'd like to give you a brief overview of how to find some simple 2 by 2 and 3 by 3 determinants. First, I want to look at some notation. So we read the determinant of A is equal to, and the symbols we use looks like the absolute value of the matrix. And so those symbols, the absolute value of A it looks like, represents the determinant of my n by n matrix A. So let's recall the formula for finding a 2 by 2 determinant. We have a matrix AB in the first row, CD in the second row. Then its determinant will be A times D minus B times C. So for example, if we want to find the determinant of the matrix 1, 2, 3, 4, then we'd simply multiply 1 times 4 and 2 times 3. Notice that as we go down from left to right with the blue arrow, it's positive, and from down from right to left, the green arrow, it's negative. So we get 1 times 4 minus 2 times 3, which is 4 minus 6, or minus 2. So the determinant of this 2 by 2 matrix 1, 2, 3, 4 is minus 2. Please note that the determinant is a scalar value, so determinants are scalars. All right, let's consider a formula for finding a 3 by 3 matrix and determinant of a 3 by 3 matrix. And there are several different ways to do this. But one way is to augment your matrix A with the columns 1 and 2 of the matrix. So if you notice that the last two columns of this augmented system have A11, A21, and A31, which is the first column of the matrix A, and A12, A22, and A32, which is the second column of the matrix A. And so we're just going to go down from left to right multiplying, and each time we multiply there, we're going to add those values. And then we'll go up from left to right all the way across, and for each of those products we will subtract those two, and that will give me the determinant of my 3 by 3 matrix. Now this is something you've probably seen in a calculus course where you're finding triple scalar products, or if you're trying to calculate the cross product between two vectors. And I just want to note that this only works for 3 by 3 matrices. So we have formulas, very straightforward formulas for finding the determinant of 2 by 2 matrices and 3 by 3 matrices, but these formulas do not work for matrices of n larger than 3. Alright, so now let's examine the effects of elementary row operations on the determinant of an n by n matrix, because as we're doing many of the things we have to do in linear algebra, we have to apply elementary row operations to our matrices, and we like to see how that impacts the determinant of the matrix. So if B is obtained by adding a multiple of one row of a matrix A to another, then the determinant of B is equal to the determinant of A. So again, B is obtained by adding a multiple of one of its rows, one of the rows of A to another, then the determinant of B is equal to the determinant of A. So let's look at an example. So consider the matrix 1, 2, 3, 4, and then 1, 2, 5, 8. And we got that as you see down there. We took 2 times row 1 and added that to row 2. Notice that the determinant of 1, 2, 5, 8 is minus 2, which is exactly the determinant of 1, 2, 3, 4. So multiplying the first row by minus 2 and adding it to the second row had no impact whatsoever on the determinant. So that's good to know, because that is probably the most often used elementary row operation when we're doing Gaussian elimination steps or trying to find inverses or other things that we're doing. And what we see is that that step, multiplying one row by some constant, adding it to another row, has no impact on the determinant of the matrix. Let's look at another example. If B is obtained by interchanging two rows of a matrix A, then the determinant of B is minus the determinant of A. So what this says is that if we interchange rows, the only way the determinant is changed is by a negative sign. So consider the matrix 1, 2, 3, 4, which we've done this example several times, and we know that its determinant is minus 2. And if we swap row 1 and row 2, we see that 3 times 2 is 6, minus 4 times 1, so that determinant is 2. So the effect of swapping rows one time was to change the determinant by a factor of -1. As you might expect, if you swapped rows an even number of times, it would have no effect on the determinant. If you swap rows an odd number of times, then it just takes the determinant and multiplies it by 1. The final elementary row operation we have to consider is if B is obtained by multiplying a row of the matrix A by a non-zero constant K. So we could multiply one row by a K, and the effect that has is that the determinant of B is equal to K times the determinant of A. So look at this example again. Again, our matrix 1, 2, 3, 4 has a determinant of -2. And if we multiply row 1 by 2, changing it to 2, 4, then we see that the matrix 2, 4, 3, 4 has a determinant of -4, which is 2 times the determinant of our original matrix. So let's summarize the effects of these elementary row operations. First, if B is obtained by adding a multiple of one row of a matrix A to another, then the determinant of B is equal to the determinant of A. Simply stated, adding multiples of rows to each other does not change the determinant of the matrix A. Secondly, if B is obtained by interchanging two rows of a matrix A, then the determinant B is equal to minus the determinant of A. Again, this just means that if we swap rows of a matrix an odd number of times, so we do an odd number of row swaps, then that will change its determinant by -1. If we swap the rows an even number of times, then the negative ones will cancel themselves out and it will have no effect at all on the determinant. And finally, if B is obtained by multiplying a row of the matrix A by a non-zero constant K, the determinant of B is equal to K times the determinant of A.